get going then. Let's move on to 5.5. 5.5, we're going to talk about linearization, sensitivity, and differentials. These are all kind of, I don't want to say off topic, but they're a little more obscure, although the linear approximation comes in very handy. So let's talk about that. So let's talk about linearization. We are at page 238 on your book. Okay. Linearization basically means that if I have a function that looks like this, I am going to, instead of, if this is the next value here, we're going to go ahead and use the tangent line at that point and to look at something that's fairly close. Let's say this guy here is going to be a delta x. If I have a small delta x here, instead of using the actual value, I'm going to use that line to approximate that value, okay? So I'm going to use the tangent line to approximate that value. And that's what linearization means, okay? So linearization is going to use a line to approximate that value that is pretty close to a next value, okay? So basically, at that line, we have what? We know that we're going to have, this is going to be f of x, right? At this point right here. So we're going to have a point. So to go through the point, this guy, and the tangent line is going to be this, obviously, right? The slope of the tangent line. So using the point slope, I get what? Y minus f of x is equal to f prime of x, x minus, okay, so let's not, so we're going to call this point A. Let's call this point A instead of using an x. So we're going to have A here, A. Okay, so f of A, right? F of A at that point, f prime A, right? And x minus A. And that's what we're going to say. So to find that value of y, we're going to say y is going to move this over, and we're going to say y is going to be f of A plus, and we're going to call it good, and we're going to call it that value, we're going to call the value for f of, instead of f of A plus delta x, we're going to use y and approximate that value. Now, obviously, there's going to be a difference here, right? You can see there's a small difference here, right? This small difference. So we're going to say that's negligible, and we're going to go ahead and use that. And so that's why it's called a linear approximation. Okay. So if you look at the bottom of that page, there's a green box that basically shows that y, or L of x, the reason that I call it L of x is because we're using a linear approximation, right? So L of x is that f of A, when x equal to A, right? So it's f of A right here, plus the f prime of A, x minus A. Okay, so that's where that comes from. All right? So I know this is a lot of, so let's go ahead and actually see what happens when we do an example, okay? Let's see what happens when we do an example. So let's do example number 1. It says, find the linearization of f of x is equal to the square root of 1 plus x. At x equals 0, at x equals 0, and I want to approximate square root of 1 plus 0.02, right? Because it's asking for 1.02, right? So that's what we're going to do. So the point that I had was when x equals to 0, what is y? Y is going to be equal to 1, right? So it's going to go through this point. So go through this point. F prime of x is going to be equal to this guy, so it's going to be 1/2 1 plus x, that, right? So when x equal to 0, what do I get here? So f prime of 0 is going to be equal to what? When x equal to 0 here, I get 1 to the negative 1/2, which is 1. So it's going to be 1/2. So the linearization of 1.02 is equal to what? I'm going to get f of 1, right? F of 0, right? F of 0 is equal to 1. And 1 plus f prime at 0, so that's going to be 1/2. Then I'm going to get what? Of 1/2 times the x. Well, x minus 0, really, right? But x is equal to what here? What are we looking at? X is equal to 0.02. 0.02, so I'm going to get 1 plus 0.01, 1.01. Okay? If you actually go into your calculator and you go 1.02, what do we get? The book says we're going to get 1.00995 something, something, something. So this is very close to 1.01. We see that the linearization is very darn close to the actual value, okay? But it's a lot easier for us to do this in our head and say, oh, it's 1.01 rather than using this number here, okay? So that is the power of this. This is the utility. This is why we use this, okay? All right, so let's see if we can go ahead and do example number 2. So the thing that's going to kind of confuse you here is that all the different nomenclatures, you have to go ahead and make that as close as, or keep track of that, all right? So in example number 2, it says a linearization of f of x equal to cosine x at x equals to pi over 2, and use that to approximate cosine 1.75. So we're trying to approximate when x is equal to 1.75. Okay, so f prime is the derivative of this, so it's going to be minus sine of x, right? So f prime at pi over 2 is going to be equal to what? Negative sine pi over 2, which is, what is sine of pi over 2? Natalie. Natalie, are you there? Where is Natalie? What happened to Natalie? She went away? I thought she was here.
I saw her, but right now she's not in this Zoom.
Caden, what's sine pi over 2?
Isn't it 1?
It's 1. You get negative 1, right? Negative 1. So let's go ahead and use that to do the thing. So L of x is equal to, what is our value at pi equals to pi when x equal to pi over 2? What is the value of this? What is cosine pi over 2? Anybody?
0.
Huh?
0.
0, right? So it's 0 here because the point that it's going to go through is, the line is going to go through is this, right? So that's that 0 there. Plus this guy here, right? Negative 1, right? Then what do I have? X minus pi over 2, correct? So we're going to get minus x plus pi over 2, where x is going to, I'm trying to approximate when x equal to 1.75. So if I put that in, I get L of 1.75 is going to be equal to negative 1.75 plus pi over 2. And if I do that, what do I get? I'm going to, well, whatever that is, right? So this is going to be your approximation right here. Right here. Okay. And again, if you plug that in, you're going to have something that's very, very darn close, where the difference is only going to be like 0.001. Okay. All right. All right. Let's go to example number 3. Now, this is the one that you really want to pay attention to, because this is where most of the time the linearization that you're going to use are going to be for this. It's going to be for the binomial powers. Binomial powers. So let's pay close attention to this one. Example number 3. Example number 3, it says, introduce a special case of the general linearization form that applies to powers of 1.1 plus x for small values of x. So what it means is that basically says 1 times 10 to the x to the k power. To the k power is going to be equal to approximately 1 times kx. Okay, which comes in very handy. So in other words, 1 plus, well, so let's go ahead and do that. Let's go ahead and do the ones that I have here. So if k is a positive integer, it follows the binomial theorem. Okay, so let's look A. We have cube root of 1 minus x. Basically look to 1 minus x to the 1/3 power. So it's basically 1 plus negative x to the 1/3 power. So if I go ahead and use this, you get 1 plus 1/3 negative x. So as you can see, you would much rather use this guy than this guy, right? You see how this is kind of not so good looking, whereas this is nice and neat, right? In other words, you got rid of the cube root thing, and you're able to say this is close enough to this.
Are you saying some numbers are prettier than others?
Yes, there are some numbers that are much prettier than others, such as, this is a nice pretty number, right? This is a pretty number too. Good question. All right, let's move on to B. B, we have, so again, if I want to express this into something that looks like this, it's going to be 1 minus x to the minus 1. So what do I get? I get 1, again, plus minus x to the negative 1, 1 to the minus 1, there times minus x, 1 plus x. So wouldn't you rather use this guy and use this guy, right? Again, okay, all right. So I can say that 1 minus 0.01, which is the same as 1 over 0.99, is approximately the same as 1.01. Again, rather than deal with this, I would rather deal with this. Okay, all right. So that is B. Let's redo C. In C, we have square root of 1 plus 5x to the 4th, 1 plus 5x to the 4th, 1/2. So this is going to be equal to 1 plus the 1/2 goes in times 5x to the 4th. Again, cleaner than that, all right? Okay, all right. And last but not least, we have D, which is 1 over square root of 1 minus x squared, which is 1 minus x squared to the negative 1/2. Approximately 1, the 1/2 goes down in there. 1/2 times negative x squared. Right? Okay, so using that, we can do example number 4. Actually, in example number 4, we're actually going to put numbers into this. Example number 4. We want to approximate a square root of 123. So this kind of, you can tell that what we're going to use is you want to use 11 here, right? You want to use 11, so this is going to be equal to the square root of 121 plus 2 type of thing here, right? Okay, all right. So x is going to be 121. So if I do f prime here, so my f of x is equal to what? F of x is equal to square root of x, x to the 1/2, right? So if I do the f prime is going to be equal to f prime of x is equal to 1/2 x to the negative 1/2. If I put 121 in here, what do I get? 121 negative 1/2. 1/2, this is going to be equal to 1/11, right? Square root of 121 is 11. There's a negative there, so it goes there. So I get 1/22. Right, so the linearization goes what? What does the linearization go like? What's the number I get? So when x equals to 121, my value is 11 here, right? So linearization of 123 is going to be equal to 11 minus, or not minus, plus this guy here, right? 1/22, right? And then I'm going to have here, what do I get? I get x. I'm trying to approximate this guy like that. So I get 11 plus 1/22, 2. So it's going to be equal to 11 plus 1/11, right? Everybody see that? Again, you're just going to have to do a lot of these. Let's do the homework. When you do the homework, it becomes a little more clear. I'm trying to kind of rattling these things off, okay? But again, it all boils down to what we talked about earlier, right? Okay. All right, so that's A, and there's another one. The other one is a cube root of 125. So the cube root of 123, I'm sorry. Cube root of 123, since we're talking about cube roots now, what's the thing that's close to 123 that we know the cube root of? What cube root do you know that is close to 123?
125.
125, right? Because the cube root of 125 is equal to what? It's 5, right? 5 times 5 times 5 is 125. Okay, so we're going to do the same thing here, right? So f of x is equal to the cube root of x. And the point that we're going to have is when x is equal to 125, it's going to be 5, right? Because that's the point that it's really close, right? Because I'm only 2 away from here, right? So I'm going to get what? F prime of x is equal to 1/3 x to the negative 2/3. This minus 1, right? Okay. So there we go. So when x is equal to 125, what do I get here? One-third, 125, negative 2/3. So I'm going to get, if I do the negative 1, if I just do the 1/3, get rid of the 1/3, what do I get? This is 1/3 of 125 to the 1/3, -2. This is going to be 5, right? This is going to be 5. 1/3, 5 to the negative that. So that's going to be what? 1/3 times 1/25, 1/75, right? That's my slope of the line at that point. So the linearization of 123 is going to be 5, right? Because it's, what's the point? The point was 125 and 5. So it's going to be 5 plus 175. Then I'm trying to do this guy, so it's 123 minus 125. So it's going to be -2, 5 minus 2/75, whatever that is. Where is it? 4.973, 4.973. Okay, again, right? Because it's close to the 5, right? It's close to the 5, right? Okay, right? Now this is kind of, again, I'm going through pretty quickly, but again, trust me, you just need to do a couple of the homework problems and it should become clear. Okay? So we are going to stop right here and then we'll do the differentials later. I mean, the second half, okay?